Okay, now we come to lecture 6. I want to introduce a tool that you will find extremely useful when you are doing physics. It can be electromagnetism, classical physics, wave propagation, quantum mechanics, or any other things. So this tool is very, very useful. So it's really a good idea to practice this tool until it becomes very natural for you, just like walking. Walking is extremely useful too, right? You walk, do you think when you walk? No, you just practice walking until it comes natural. Okay, so this tool is called linearize function. Linearize function. It enables you to solve many physics problems which otherwise you cannot solve. Of course, when I say solve, it includes exact solution or approximate solution. Okay, in physics, very often we cannot get exact solution, but we are satisfied with approximate solution. Okay. Now, linearize function. Okay. Let me give you a function that is very hard to solve. Okay, so we want to do this. Suppose we want to this is just an example. Suppose we want to do an integral. Okay, minus a to a and exponential of x over r. I will explain the term shortly. Okay, this is the integral we want to solve. E one bracket dx. Okay, this is an integral that is not easy to integrate by hand. And let me explain all this symbol, right? Okay, x is the variable, right? And then let, in this example, let r equals to, let's say, 10,000. Okay, equals to 10 to the 4. Let a equals to 0.1, let's say. Okay, all right. So immediately, whatever this function is, let me plot roughly this function. Okay, this is not a really correct plot. Okay, this is we call fx. This is not really a correct plot. Okay, from minus 0.1, 0.1, right? So this look like some exponential of something. Okay, something like this. Okay, you want to find area under curve, right? Integral area under the curve, right? Some function like this. Okay, fx suppose. Okay. So it's very difficult, right? You want to find area under the curve. Okay. So what do? We do an approximation. Why we do an approximation? You look at this. Let lambda equals x over r. Okay. You know, in this integral, x range from a to minus a, right? A to minus a dx. Okay, so x over r range from 0.1 divided by 10,000 to minus 0.1, 10,000. All right, so x over r is lambda, right? So x over r is lambda. This one is 10 to the minus 5 minus 10. Okay, first we establish that lambda is small. Small means lambda is much less than 1. Okay. Lambda magnitude is much less. We establish this. Okay. First point, right? First point was our integration. Okay. Now, let me write fx equals to exp x over tangent. Okay, this is exp x over r is lambda, right? Okay, we have everything in terms of lambda, so we just write f lambda, okay? And here we have this integral, you see? So x over r equals lambda. Ex equals to r e lambda. Okay, now we write the integral. And the limits of integral is so we write this integral. Okay, let me rewrite this a bit so that you can compare and contrast. Okay, this is the original integral we set up solve, but we write this integral in terms of lambda. Dx, we become d lambda, right? A become 10 minus 5, 10 to the 5. Okay, the exp become lambda tangent lambda plus 1. Okay. Again, I want to say that you look through this lecture and then you go practice like 10 times. Okay, 10 times. As you practice, you remind yourself what's the mechanism, what are the steps, what is the reason for the steps. Okay. Now, is again f lambda. Okay. And we want to do Maclaurin series. Maclaurin series is that equal to expand about 0. Lambda f from 0 plus lambda squared of f from 0 plus lambda cube over 3 factorial f from 0 and so on. Okay, so now we have constant term. We have linear term, lambda term. We have quadratic term, lambda square term, and so on. So let me write this as, because lambda is small, okay, lambda is small. Plus, we use a notation. Everything is lambda square term, lambda square. It is this everything here up to infinite. I summarize is this. Okay. All right. Order. This big O is called order, right? Order, right? Okay. Now we are in business, right? F lambda equals to exp lambda tangent lambda plus 1. F0, F lambda, right? F lambda, F0 equals to exp0 tangent 0 plus 1. This is exp0 equals to, okay. All right. So we differentiate this guy. Differentiation is much easier than integration. We can differentiate almost all the things that we encounter. We differentiate this and then we use chain rule. Differentiate exponential is exponential. Chain rule. And we differentiate the inside. Differentiate lambda, then the inside will product rule. So differentiate lambda, keep the tangent. Plus differentiate the tangent, keep the lambda. Differentiate tangent, we get secant square. Okay. Okay. Now f prime 0, you substitute 0 inside xp, same story. Substitute 0 inside lambda 0 plus 1 plus 0 times secant square 1, 0 plus 1, right? Then we work through every steps. You should work through every steps. exp0 is 1. Tangent 0 plus 1 is tangent 1, right? 1 radian. 0 times secant square 1 is 0. Okay. Now we are left with tangent 1. Good. Now come back to my current series. We have this term. F lambda equals to F0 0 plus lambda F prime 0 plus order of lambda square. This one we know is small. Lambda is small. Lambda square is smaller. F0 equals to 1. F prime square equals to tangent lambda plus order square. Okay. I'll come back to the integral. This is what we want to do. Integral 10 minus 5, 10 5 plus f lambda d, right? You substitute f lambda to be 5. Substitute needs to be 1, tangent 1, lambda e lambda plus minus 10 minus 5, 10 minus 5. Some lambda, square lambda, cube lambda, the power of 4 thing, right? I call this lambda square e lambda, right? So this is small because you see lambda is co-range from this. This is small. So this whole thing is small. Okay, now we are left with this. Okay, there's only one integral here. This come out, don't know why. So it's easy, right? It's easy. So we will have integral minus 10 minus 5, 10 minus 5 times 1 e lambda. And ignore this stuff, right? Right? Ignore. No. How do you spell it? This is equal to plus tangent 1 lambda e lambda, right? Roughly equals to, because we drop the small term. So this is easy. This is 2, 10 minus 5. Oh, wait, I missed something. Huh? Integral. Go back. There's R here. God. This R here. Take out R. Okay, take out R. Okay. Recall that R equals 10 to the 4. R here. R here. Plus R. 1. 5. 10 5. Lambda d. Okay. Okay, yes, correct. Lambda d lambda. You plot this curve, it is lambda. This curve, right, is straight line. We integrate from 10 minus 5 to 10 minus 5. Area under curve equals 0, right? This term equals to this term equals 0. Okay, equals 0. 0. Okay, it's linear function. So we left with this term, and R is 10 to the 4 times 2 times 10 minus 5. So the whole integral I put back, okay, in terms of x. Okay, let's write out. This terrible integral, right? Will be equal to minus 10 minus 5 or 10 minus 5 xp lambda tangent lambda plus 1 is exactly equal. And then we do approximation here, right? We do approximation. Where's the approximation, right? It's this one. We just write approximation. It's this one. 1 tangent 1 Okay, this become this 2 times 10 minus 1, right? Plus integrate this guy, you get 0 because you integrate the odd function, this one, right? 0. Okay. So voila, the answer is 0, 2. Okay. So this integral roughly equals to 0.2 to some approximation. Okay, done. We are done. Okay, what's the lesson here? This integral is very difficult. We convert it to some integral of some small number. Okay, small, right? Lambda is small. Okay. So this integral is very difficult. And then we use Maclaurin series. We make it linear plus order lambda square. And then we drop this down because it's small. Lambda is small, lambda square is smaller. Okay, so we keep this down. Then we come to here. Then everything is easy. Okay, it makes sense. Okay, so this is called linearize. Why is called linearize? Because f lambda is not a linear function, right? Linear function means f lambda this linear function. It's called L. L lambda is a linear function. Is a let's say don't use a, right? Let's say it's b plus c lambda. This is linear. This lambda power 1. Don't have lambda power 2. Okay, this is linear. Okay, so f is not linear, but we approximate it using Maclaurin series to become linear. We can only do this when we know lambda is small. It's always small. So when we want to solve an equation, you look at, okay, this gigantic equation like a monster. Then you look at what is small in this equation. Then you get it, right? You can linearize. This is linear function. Okay. All right. With this, we end the lecture, but I want to emphasize again, linearize a function is extremely useful and powerful. So you need to practice and then practice again and then practice again and again and again and again and again until when you do this, you feel like, oh, it's as easy as walking. Okay, become natural. It's like walking. Okay, and then your physics will be very powerful, extremely powerful. Okay, all right. There are other tricks I will talk about next time in the future. For now, one thing at a time. You learn one thing at a time. You learn this trick, linearize a function. Okay, with this, we can end the lecture. Thank you.